So chapter 13 is all about kinetics, right? And we're going to have to find rate laws a lot. So number 43 from the back of the book of chapter 13 in the back of the chapter, we have to write an expression for the reaction rate law and calculate the value of the rate constant K. And it's asking for the overall order of the reaction. You have to refer to the chart in your book. So if you want to open up to that chart, that would be really good. The problem has all the information. I kind of recreated one a little bit here. It might be in a different order with NO2 and F2, but the data is the same right here. So if you want to use the chart in your book, it'd probably be easier to read. So to find the reaction rate law, and this is, remember, of multiple reactants, right? We have NO2 and F2. So our general formula, right, we can deal with is in the form of rate, color y'all can see. Our general formula really is focusing on rate equaling K times the two different products, right? So rate will equal K, our rate constant, times NO2 to some power M times F2 to some power N. Now remember, M plus N is your overall order. Overall order of the reaction, right? So we're trying to figure out M and N so we can add them together. And how do we do that? We have to look at the information given in the table about different concentrations, right? Remember, brackets meaning concentrations. So, and we're going to find K. So basically we have three values. We're looking for the fourth, the K. Now, using this table is what's really important. So we have to figure out M and N. And remember, it's going to be usually like a first order or second order or zero order. So if we look at the numbers, we have 0.026, 0.051, and 0.103. Now, NO2 and F2. So we have to look at something where one of them stays the same. So if we look at the first two, 0.01 and 0.01 for F2. They're staying the same. So what only changed was NO2. That went up times 2, right? NO2 went up by 2. And what happened to the rate? It went roughly from 0.026 to 0.051. And remember, if we do the math, that's also roughly by 2. So what kind of reaction does that represent? If you double the concentration, you double the rate, that's a true definition of a first order reaction. So we know that M will equal 1. Now you can also do the math to prove it. You can you can do the whole rate 2 over rate 1, and you can put out both these formulas and everything will cancel. But this, I'm not going to do that because we already know what the rate M is going to be. We can do the same thing to find N. We're going to look at F2. Now if we hold NO2 constant, which is the first one to get M, right, we can look at F2. And so here, they did not change, and instead, F2 changed by 2. It went up by times 2. And what happened to the rate? It went up also, it doubled from 0.05 to 0.1, right? So we also know that F2 is going to be a first order reaction because when we doubled the concentration, the rate doubled, and we didn't change NO2. So we can deduce both of the M and N's from there. So our overall is going to be a second order, right? 1 plus 1. Is a second order. Now, from here is where it gets a little bit trickier. So we have to deal with two different things. Sorry, I'm trying to find a pen. So we have M is equal to 1 and N is equal to 1. Make it a little darker for you. And our overall is 2. So we found the overall reaction order. That's done. We need to find K. So we have an expression is right here, right? So we're going to say rate is equal to K times the concentration of NO2 to the first times the concentration of F2 to the first. That's our expression. So we can plug in different values off our table, remember, to find K. So let's do it the first time. Let's do it with experiment 1. If we use these values, we're going to put in rate of 0.026, solve for K. Concentration of NO2 is 0.01, raise it to the first, times 0.01, raise it to the first. And if we solve for that, move it all around, and K will equal roughly 2.57 molar second per molar second, right? 1/1. Yeah, okay. So we have 2.57 is what this one's looking at. Now we can also use the other formula. You could have used the second formula if you needed to. You can have plugged in 0.051 is equal to K, yeah, I shouldn't forget K, times 0.02, times 0.2, sorry, to the first times 0.1 to the first. And we'd have solved for K and you would get just about the same answer as that. So they're going to equal the same thing. So we figured out it's 2.57. So our overall, you can rewrite it filling in K, is rate is going to be 2.57 per molar inverse second, times the concentration of NO2 to the first, F2 to the first. So that's our overall reaction order. Reaction constant times this, right? The K. So that's just a different way of doing that. Make sure you look at the chart in your book to figure that out. You can deduce these by that as well. And so that's how we got our reaction rate law and the value of constant K and the overall reaction order.